The Imperial Japanese Navy's I-400 carried enough fuel to circle the globe 1.5 times without resurfacing. American intelligence officers who examined the captured vessel in 1945 could not understand how a submarine this massive, 400 feet of welded steel, could dive at all, much less remain submerged for days while Allied destroyers prowled overhead. The answer lay not in engine technology or battery chemistry, but in a hull design so counterintuitive that Western naval architects had dismissed it as structurally impossible. Before we go deeper into how this decision changed the Pacific War forever, make sure to subscribe for more history that actually happened. The paradox begins in 1922, in the smoking rooms of the Washington Naval Conference, where Japan's admirals sat across mahogany tables from their American and British counterparts and agreed to permanent numerical inferiority. The treaty limited Japan's battleship tonnage to 60% of the Anglo-American standard, a mathematical humiliation that transformed Japanese naval doctrine overnight. If surface parity was forbidden by international law, the Imperial Japanese Navy would seek supremacy beneath the waves. In the Kure naval arsenal's drafting halls, engineers began sketching submarine designs that violated every convention of Western naval architecture. The Japanese had inherited their submarine tradition from contradictory sources. Early boats came from Britain's Vickers yards, compact, single-hull designs optimized for the North Sea's shallow waters and short patrol distances. But the Pacific demanded different mathematics. From Yokosuka to Wake Island stretched 3,500 nautical miles of open ocean, distances that exhausted British-pattern submarines before they reached operational areas. The answer arrived as war reparations from defeated Germany. 7 U-boats crossed to Japan in 1919, including examples of the Mittel'u and the massive U-cruisers that had terrorized Atlantic shipping. Japanese engineers studied these boats with obsessive precision, measuring every weld, photographing every valve, calculating the volume ratios between pressure hull and external tanks. What they discovered was architectural heresy by British standards. German submarines used double-hull construction, an inner pressure hull to resist sea pressure, surrounded by an outer hydrodynamic shell with ballast and fuel tanks in between. British designers rejected this approach as wasteful, adding structural weight that reduced diving speed and complicated damage control. But the Germans understood something the British did not: the space between hulls could serve triple duty as ballast reservoir, fuel storage, and protective buffer against depth charges. For operations in the Pacific's vast distances, this inefficiency became strategic necessity. The first truly Japanese design incorporating these principles emerged in 1924 as the Junsen type, with Lieutenant Commander Kishimoto Keinuki directing the project under supervision of Dr. H. Teschel from Krupp's Germania Yard. The J-1 class stretched 300 feet with a surface displacement of 2,300 tons, dimensions that seemed absurd for a submarine until engineers explained the internal arrangement. 2 parallel pressure hulls, each 9 feet in diameter, ran the length of the boat like a figure 8 turned horizontal. This configuration distributed sea pressure across 2 smaller cylinders rather than one large one, allowing deeper diving with thinner steel. Between the pressure hulls and the external streamlined casing lay fuel bunkers holding 580 tons of diesel oil, enough for 25,000 nautical miles at 16 knots surfaced. The design's genius revealed itself in operational endurance calculations. An American fleet submarine like Gato carried fuel in internal tanks that displaced battery space and crew quarters. Japanese boats stored fuel externally in the double-hull gap, preserving interior volume for larger battery banks and longer-range torpedoes. This architectural choice created a cascade of tactical advantages that American naval intelligence would not fully comprehend until 1943, when systematic analysis of captured boats began. Consider the battery mathematics that governed submarine warfare in 1941. Every hour submerged drained lead-acid cells that could only be recharged by running diesel generators on the surface, exposing the boat to aircraft and destroyer patrols. The Gato class mounted 2 battery groups of 126 cells each, providing 48 hours of underwater endurance at 2 knots, barely walking speed. Japanese Type KD-6 boats carried similar battery configurations but achieved different results through hull design. The double-hull structure allowed engineers to mount batteries lower in the hull, improving stability while submerged and permitting slightly higher underwater speeds without proportional power drain. More critically, the external fuel storage meant Japanese submarines could remain on station longer before returning to base. A Gato-class boat departing Pearl Harbor for the waters off Truk consumed one-third of its fuel reaching operational range. The equivalent Japanese I-class boat, sailing from Kwajalein to patrol off Midway, retained two-thirds of its fuel for station keeping and attack runs. This fuel efficiency did not result from superior engine technology. Japanese diesel plants actually lagged behind American designs in power-to-weight ratio, but from architectural decisions made 2 decades earlier in the Kure drafting halls. The figure-8 pressure hull configuration created another advantage that American designers never fully appreciated. When depth charges detonated near a single-hull submarine, the shock wave struck the pressure hull directly, potentially cracking welds or loosening rivets. Japanese double-hull boats absorbed the same explosions differently. The outer hull buckled and tore, the space between hulls flooded, but the inner pressure hull remained intact if the crew flooded counterbalancing tanks quickly enough. Lieutenant Hashimoto Mochitsura, commanding IA-58, survived depth charge attacks that would have crushed single-hull boats, crediting his survival to the layers of steel that kept the ocean at a distance while we lay on the bottom like a wounded animal. The construction process for these boats bordered on industrial art. At the Kawasaki shipyard in Kobe, workers built pressure hulls from rolled steel plates 18 mm thick, electric welded rather than riveted to prevent stress concentrations. Each weld underwent ultrasonic inspection, a technology borrowed from German practice. The outer hull used thinner steel, 12 mm, shaped over oak frames to create the streamlined form that reduced drag when surfaced. Between these hulls, welders installed the complex maze of fuel tanks, ballast tanks, and trim tanks that made the boat operational. Fuel management demanded extraordinary attention. The bunkers between hulls held diesel oil at ambient sea pressure, meaning water pressure at depth squeezed fuel into compensating tanks as the boat descended. Surfacing reversed the process, diesel flowing back into the bunkers as external pressure decreased. This system eliminated the need for pumps to transfer fuel, saving weight and reducing mechanical complexity, but required meticulous calculation to maintain proper trim at all depths. Submarine commanders learned to feel their boat's balance through their feet, sensing when fuel distribution was becoming dangerously asymmetric. The earliest submarine warfare had consisted of desperate improvisation. During the Russo-Japanese War of 1904, Japan purchased 5 Holland-type submarines from the United States, shipped in knockdown sections by rail from Seattle to avoid alerting Russian intelligence. These boats displaced barely 100 tons and could barely dive to 50 feet. Their gasoline engines created explosive fumes that killed more crews in accidents than died in combat. Yet they established the precedent that submarines could be decisive weapons in Pacific warfare, a lesson Japanese naval planners never forgot. By the 1920s, submarine technology had advanced dramatically. Diesel engines replaced gasoline, eliminating the explosive vapor problem. Electric motors powered by lead-acid batteries enabled underwater propulsion. Periscopes allowed commanders to observe surface targets without exposing the boat. Torpedoes increased in range and reliability. But the fundamental constraint remained: diesel-electric submarines were surface ships that could temporarily submerge, not true undersea vessels. They spent 90% of their operational time on the surface, vulnerable to aircraft and destroyer attack. The Kaidai-class submarines of the late 1920s represented Japan's first systematic implementation of double-hull principles on a production scale. The KD-1 through KD-7 variants displaced between 1,500 and 2,000 tons surfaced, with fuel capacities ranging from 300 to 450 tons. These boats could patrol for 60 days without replenishment, covering 14,000 nautical miles at 10 knots. Their double-hull construction placed saddle tanks along the boat's sides, creating the distinctive external bulges visible in period photographs. Engineers at the Yokosuka Naval Arsenal calculated that every ton of fuel stored externally freed 17 cubic feet of internal volume for other uses. Across a 1,500-ton boat, this meant an additional 250 cubic feet available for batteries, torpedoes, food storage, and crew comfort. The mathematics seemed trivial until multiplied by weeks at sea. Extra battery capacity meant 1 additional hour submerged per patrol. Extra food storage meant 1 fewer supply rendezvous. Extra torpedo space meant one more attack opportunity. These marginal gains accumulated into decisive advantages during extended operations. The Type 93 long-lance torpedo, developed in parallel with the Kai-Dai submarines, demonstrated how weapons design interacted with hull architecture. This oxygen-fueled weapon measured 29 feet long and weighed 5,900 pounds, far larger than American Mark 14 torpedoes. Japanese boats needed external cradles to carry reload torpedoes because the Type 93 size would have consumed excessive internal volume. The double-hull design accommodated these cradles naturally, with torpedo storage tubes built into the space between pressure hull and outer casing. Testing protocols for new submarine designs consumed years of careful experimentation. The Kure Naval Arsenal maintained a test range in Hiroshima Bay where prototype boats underwent systematic evaluation. Engineers measured diving times, turning radiuses, and stability characteristics under varying load conditions. They simulated combat damage by flooding specific tanks and measuring the boat's response. They ran engines to destruction to establish maintenance schedules. This empirical approach produced reliable boats but delayed production, a trade-off Japanese planners accepted in pursuit of technical excellence. The IA-15 class, launched between 1938 and 1940, represented the apex of pre-war Japanese submarine development. These boats displaced 2,500 tons surfaced and carried fuel for 14,000 nautical miles at 16 knots. Their double-hull construction featured a pronounced figure-8 pressure hull cross-section, with crew quarters and machinery split between the two cylinders. This arrangement provided redundancy. If one pressure hull section flooded, the other might remain intact, but complicated internal communication and damage control. Crew training emphasized the unique characteristics of double-hull boats. Sailors learned to interpret the sounds of water flooding external tanks, distinguishing between planned ballast operations and combat damage. They practiced emergency procedures for situations unique to double-hull designs, outer hull breaches that flooded the inter-hull space, asymmetric flooding that created dangerous list angles, and fuel leaks that contaminated ballast tanks. These scenarios rarely affected single-hull boats but could prove catastrophic in double-hull designs. The Pacific War's opening phases showcased Japanese submarine capabilities and limitations with brutal clarity. On December 7, 1941, 5 Type A midget submarines attempted to penetrate Pearl Harbor alongside the aerial attack. These small boats used double-hull construction in miniature, with external ballast tanks surrounding a central pressure hull barely 10 feet in diameter. All 5 were lost, victims of their slow diving speed and limited underwater endurance. The double-hull design that worked well in large ocean-going boats proved inadequate when scaled down to midget dimensions. Full-sized Japanese submarines fared better initially. The IA-6 torpedoed and damaged USS Saratoga in January 1942, putting the carrier out of action for months. The IA-168 sank USS Yorktown after the Battle of Midway, finishing off the damaged carrier with Type 93 torpedoes. The IA-19 achieved the war's most successful submarine attack in September 1942, firing a 6-torpedo salvo that sank USS Wasp, damaged USS North Carolina, and destroyed USS O'Brien, 3 major warships from a single spread. These victories demonstrated that Japanese submarines could execute their designed mission of attacking enemy battle fleets. But strategic success eluded the Japanese submarine force despite tactical victories. American submarines, meanwhile, pursued systematic commerce raiding that strangled Japan's seaborne logistics. Gato and Balao-class boats sank tankers carrying oil from the Dutch East Indies, freighters hauling bauxite from Malaya, and transports moving troops between island garrisons. This campaign devastated Japan's war economy far more than the occasional sinking of a warship could. The fundamental problem lay not in hull design but in doctrine. Japanese submarines were optimized for fleet engagements against enemy warships, a mission that matched naval tradition but ignored strategic reality. The double-hull design's extended range should have enabled blockade operations across the Pacific's shipping lanes. Instead, Japanese boats concentrated near Allied naval bases, waiting for opportunities to attack heavily defended battle groups. American anti-submarine warfare improved rapidly, radar-equipped destroyers and patrol aircraft making these attacks increasingly suicidal. The IA-400 class embodied both the ambition and futility of Japanese submarine strategy. Conceived in 1942 when Japan still held strategic initiative, these boats were designed to strike the Panama Canal with aircraft-delivered bombs, closing America's interocean transit route. Each boat displaced 6,500 tons submerged and stretched 400 feet from bow to stern. The double-hull construction reached Baroque complexity, twin pressure hulls in figure-8 configuration, external fuel bunkers holding 1,600 tons of diesel, and a massive aircraft hangar running 115 feet along the foredeck. Construction of the IA-400 class revealed the strengths and weaknesses of Japanese shipbuilding during the war's final years. Workers at Kure Naval Arsenal maintained quality standards comparable to peacetime construction. Welds received full radiographic inspection. Pressure. Hull plates met thickness specifications. Machinery underwent complete testing. But material shortages forced compromises. The outer hull used lower-grade steel than specifications called for. Some fuel tank baffles were eliminated to save weight. Electrical systems substituted cotton insulation for synthetic materials unavailable in blockaded Japan. The aircraft carried by the IA-400 boats, HEM-6A Siren float planes, showed similar patterns of ambitious design and compromised execution. Each plane carried a 1,760-pound bomb or torpedo, sufficient to damage the Panama Canal locks if delivered accurately. The aircraft folded ingeniously to fit in the submarine's hangar, wings folded against fuselage, horizontal stabilizer rotated vertical, floats detached and stowed separately. Unfolding and launching 3 aircraft required 25 minutes, an eternity when surfaced in hostile waters. The double-hull design provided stable floating platform for launching operations, but also created a massive target visible for miles. Combat patrol reports from Japanese submarines document the grinding attrition of submarine warfare. Boats departed on 60-day patrols carrying provisions for 80 days, the extra 20 days insurance against delayed returns. Crews endured tropical heat without air conditioning, temperatures inside pressure hulls reaching 120 degrees Fahrenheit when submerged in equatorial waters. The double-hull construction that provided combat advantages also trapped heat between the hulls, turning boats into steel furnaces during extended submerged periods. Mechanical reliability plagued Japanese submarines throughout the war. Diesel engines required overhaul every 1,000 hours of operation, a maintenance interval that exceeded Pacific patrol durations but forced periodic returns to base. Electric motors failed when saltwater contaminated their windings, a common problem in boats where hull penetrations leaked under depth charge concussion. Battery cells developed shorts that reduced capacity and created explosive hydrogen gas. Each breakdown shortened patrol endurance and forced premature returns, negating the range advantages the double-hull design provided. The Battle of the Philippine Sea in June 1944 illustrated the diminished effectiveness of Japanese submarines by mid-war. American carrier task forces operated with destroyer screens that detected submerged boats at ranges exceeding torpedo launch distances. Radar-equipped aircraft patrolled continuously, forcing submarines to remain submerged during daylight. The IA-184 attempted to attack USS Bunker Hill but was detected and driven deep by destroyers. The boat survived depth charging but expended so much battery power evading that it had to return to base without attacking. Similar failures occurred across the Japanese submarine force, boats with adequate range and weaponry unable to penetrate American defenses. American anti-submarine tactics evolved to exploit Japanese submarine weaknesses. Destroyer depth charge patterns were calibrated to reach 400 feet, deeper than most Japanese boats could safely dive despite their double-hull construction. American submarines began hunting Japanese submarines, using superior sonar to locate targets and superior fire control to sink them. The USS Batfish famously sank 3 Japanese submarines in 4 days in February 1945, detecting them on surface radar while they transited at night to recharge batteries. The double-hull design's protective benefits diminished as American depth charges grew more powerful. Early war depth charges carried 300 pounds of explosive. By 1944, charges held 600 pounds, creating shock waves that breached both outer and inner hulls simultaneously. The IA-44, sunk in April 1945, suffered catastrophic hull failure when a destroyer dropped a full pattern directly overhead. Post-war analysis of the wreck showed both pressure hulls had failed at the same frame station, the double hull design providing no additional protection against such massive explosions. Fuel quality problems intensified as the war progressed. Japanese refineries produced diesel oil contaminated with water and sediment, requiring careful filtration before use. The external fuel bunkers on double-hull boats allowed water infiltration through minute leaks, further contaminating fuel. Crews learned to drain water from bunker bottoms before transferring fuel to day tanks, adding another maintenance task to already overburdened damage control parties. Some boats experienced engine failures from contaminated fuel while on patrol, rendering them unable to charge batteries and forcing dangerous long-distance underwater transits back to base. The I-58's final patrol in July 1945 demonstrated that well-handled Japanese submarines remained dangerous despite overall force deterioration. Commander Hashimoto Mochitsura took his boat into the Philippine Sea with orders to attack American supply convoys. On the night of July 29, lookouts spotted USS Indianapolis transiting alone at 17 knots. Hashimoto ordered a 6-torpedo spread fired at midnight range. 3 torpedoes struck, breaking the cruiser in half and sending 900 men into the water. Only 317 survived 5 days awaiting rescue, the remainder lost to exposure and shark attack. The attack succeeded because I-58's double-hull design enabled it to remain on patrol long enough to encounter Indianapolis. The boat had been at sea for 3 weeks, diving during day and surfacing at night to recharge batteries. Its external fuel bunkers still held sufficient diesel for 2 more weeks of operations plus the transit back to Kure. This endurance meant Hashimoto could patrol an area until targets appeared rather than having to return to base prematurely like shorter-range boats. The double-hull design delivered exactly what its creators intended, extended patrol capability that increased probability of encountering targets. But this success came too late to affect the war's outcome. Indianapolis had already delivered its cargo, components of the atomic bombs destined for Hiroshima and Nagasaki. Japan would surrender 2 weeks after the sinking, rendering all subsequent submarine operations meaningless. The I-58 survived the war and was scuttled by American forces in 1946, ending its career like most Japanese submarines, technically successful in execution but strategically irrelevant. American examination of captured Japanese submarines after the war produced detailed technical intelligence that influenced submarine design for decades. Engineers at the Naval Technical Mission to Japan measured every aspect of the IA-400, IN-401, and smaller boats captured intact. They calculated the volume ratios between pressure hull and external tanks. They tested the strength of welded joints. They analyzed the fuel transfer systems that allowed diesel to flow under sea pressure. The conclusion was unambiguous: Japanese double-hull construction provided genuine advantages in specific operational scenarios. The figure-8 pressure hull cross-section particularly interested American naval architects. This configuration distributed sea pressure more evenly than circular cross-sections, potentially allowing deeper diving with less steel. American designers calculated that a figure-8 hull of equivalent strength to a circular hull could save 12% of structural weight. However, the figure-8 design complicated construction, requiring custom frames and more complex welding sequences. American shipyards, optimized for mass production of standardized designs, could not economically adopt these techniques. External fuel storage showed more promise for American adoption. Post-war submarine designs began incorporating external fuel bunkers, particularly in nuclear boats where reactor shielding consumed enormous internal volume. The principle remained the same: storing fuel. Outside the pressure hull freed internal space for more critical functions. American engineers improved on Japanese practice by using double-walled tanks that prevented fuel contamination from seawater leakage, addressing one of the major problems Japanese boats had experienced. Soviet submarine designers, denied access to captured Japanese boats, developed similar double-hull designs independently based on German U-boat technology. The Whiskey-class submarines of the 1950s used figure-8 pressure hulls and external fuel bunkers nearly identical to Japanese practice. Whether this represented parallel evolution or successful intelligence acquisition of Japanese plans remains debated. Declassified Soviet documents suggest their designers had access to Japanese technical manuals captured by Red Army forces in Manchuria. The nuclear submarine revolution of the late 1950s rendered many of these architectural debates obsolete. Nuclear reactors eliminated the need for large diesel fuel bunkers. High-pressure steam turbines provided unlimited underwater propulsion without battery recharging. The fundamental constraint of diesel-electric boats, limited submerged endurance, vanished overnight. Double-hull construction survived primarily in Soviet practice, where it persisted into the 1990s more from institutional momentum than technical necessity. Modern historical analysis of Japanese submarine operations focuses on the disconnect between technical capability and strategic employment. The boats themselves represented sophisticated engineering that solved real problems in range, endurance, and survivability. The double-hull design delivered measurable advantages in operational tests. Japanese submarine construction quality equaled or exceeded American standards in many areas. Yet all this technical excellence was squandered on a strategic approach that emphasized fleet combat over economic warfare. Consider the mathematics of alternative strategies. Japan began the war with 63 ocean-going submarines capable of extended patrols. If these boats had concentrated on commerce raiding rather than warship hunting, they could have maintained continuous blockades of multiple Australian ports simultaneously. Each boat sinking one merchant ship per month would have destroyed 750 vessels over the war, potentially severing Allied supply lines to the Southwest Pacific. The double-hull design's extended range made this strategy feasible in ways that would have exhausted shorter-ranged boats. Instead, Japanese submarines sank fewer than 200 Allied merchant ships total, focusing on heavily defended warships that represented difficult targets with limited strategic value. Individual attacks sometimes succeeded spectacularly, but systematic pressure on Allied logistics never materialized. American submarines, meanwhile, sank 1,300 Japanese merchant ships totaling 5 million tons, starving the home islands of raw materials and food. The strategic asymmetry was total. Japanese submarines designed for long-range operations frittered away their advantages on opportunistic attacks while American boats executed systematic economic warfare. The human cost of this strategic failure appears in casualty statistics. Japan lost 130 submarines during the war, taking approximately 10,000 sailors to their deaths. These men operated sophisticated equipment competently, often displaying remarkable courage under impossible conditions. But bravery cannot compensate for strategic confusion. The crews who died in depth-charge attacks off Guadalcanal or aircraft strikes near Truk were victims of doctrine that sent them into the most dangerous waters to hunt the most difficult targets. Individual Japanese submariners demonstrated exceptional skill that circumstances rendered futile. Commander Hashimoto's midnight approach on Indianapolis showed tactical mastery of submarine attack procedures. Lieutenant Zenji Orita, commanding IA-47, successfully penetrated Ulithi Harbor in November 1944 using Kai-10-man torpedoes to sink the oiler Mississinua, displaying courage and navigational precision. But these isolated successes paled beside the systematic campaign American submarines waged against Japanese merchant shipping. The final months of the war saw Japanese submarines relegated to supply missions, ferrying food and ammunition to isolated garrisons bypassed by American forces. The IE-361 class boats, designed specifically for cargo transport, converted their torpedo rooms to cargo holds and made desperate runs to islands like Rabaul and Truk. These missions utilized the double-hull design's range advantages but represented the opposite of the boat's intended purpose. Submarines that could have strangled Allied supply lines instead became glorified cargo vessels carrying rice to starving garrisons. American bombing of Japanese shipyards accelerated submarine force decline in 1945. The Kure Naval Arsenal, primary construction site for large submarines, suffered devastating air raids in March and July that destroyed partially completed boats and damaged repair facilities. The IU-402, third of the IU-400 class, was never completed, her hull resting on building ways when the war ended. Workers had installed the pressure hulls and were fitting the outer hull when orders came to suspend construction. The surrender on August 15, 1945, left Japan's submarine force scattered across the Pacific. Some boats were at sea when the announcement came, their crews faced with the choice of continuing to fight or obeying the Emperor's command. The I-58, Hashimoto's boat, was near Kyushu preparing for attacks on invasion fleets that never came. The I-400 and I-01 were in the inland sea, their planned attack on the Panama Canal cancelled weeks earlier. The I-14 was undergoing repairs at Sasebo. All would be surrendered to American forces and eventually scuttled to prevent Soviet examination. The scuttling of the I-400 class boats occurred in 1946 after American engineers had completed their technical examination. The submarines were towed to deep water off Oahu and sunk by demolition charges. They went down in more than 2,000 feet of water, taking with them the ultimate expression of Japanese double-hull submarine design. Modern deep-sea surveys have located some wrecks, revealing that the boats remain largely intact on the seafloor, their double hulls corroded but still recognizable. Legacy of the double-hull design persists in specialized applications. Modern diesel-electric submarines built for extreme range sometimes incorporate external fuel storage, particularly boats designed for operations in the Indian Ocean or Southern Pacific. The physics remain unchanged, storing fuel outside the pressure hull preserves internal volume for batteries, weapons, and crew. But modern materials and construction techniques eliminate many problems that plagued wartime Japanese boats. Educational institutions preserve the memory through museum exhibits and cutaway models. The Maritime Self-Defense Force maintains a submarine museum at Kure that includes detailed models of I-class boats showing internal arrangements. These displays teach current generations how earlier engineers solved problems of range and endurance through innovative hull design. The technical achievements receive proper recognition even as strategic failures are acknowledged. The final accounting reveals technology that succeeded technically but failed strategically. Japanese double-hull submarines performed as designed, diving deeper and patrolling longer than many Allied boats. The figure-8 pressure hull distributed sea pressure efficiently. The external fuel bunkers provided range for transoceanic missions. Construction quality ensured boats remained operational through years of combat. Yet none of this mattered because strategic doctrine deployed these sophisticated platforms on missions that wasted their capabilities. Superior engineering cannot rescue flawed strategy, a lesson that transcends naval warfare and applies wherever means become disconnected from ends. If this story gave you a new way to see the Pacific War, like, share, and subscribe, and tell us which moment surprised you most. We'll return next week with another chapter in the war that changed the world. The technical specifications that defined Japanese submarine superiority in certain parameters began with metallurgy. The Kure Naval Arsenal developed a specialized steel alloy designated NS-46, indicating 46 kilograms of pressure resistance per square millimeter. This high-tensile steel allowed thinner pressure hull plates than conventional shipbuilding steel while maintaining equivalent strength. A single-hull American submarine required 21mm plates to reach 300 feet safely. Japanese double-hull boats achieved similar depth ratings with 18mm plates in the pressure hull, saving approximately 4 tons of steel per boat. That weight savings translated directly into additional fuel capacity or battery cells. The welding techniques used in pressure hull construction represented another Japanese innovation. Traditional submarine construction used riveted seams, creating stress concentration points where metal fatigue could initiate cracks. Japanese yards adopted electric arc welding for pressure hull seams in the late 1930s, joining plates without the structural weaknesses rivets introduced. Each weld underwent visual inspection for surface defects, followed by ultrasonic testing that detected internal flaws invisible to the eye. Welds failing either test were ground out and re-welded until they met specifications. This quality control slowed production but produced hulls capable of exceeding their rated depth by 50% without failure. The saddle tank configuration that characterized Japanese double-hull designs required precise hydrodynamic calculation. Water flowing over a submarine's hull creates drag proportional to the hull's wetted surface area. Double-hull boats had more surface area than single-hull designs. Of equivalent internal volume, creating higher drag and reducing surface speed. Japanese naval architects minimized this penalty by shaping the outer hull to minimize turbulent flow. They installed streamlined fairings where saddle tanks joined the main hull, reducing vortex formation. They positioned limber holes, openings allowing water to flood ballast tanks, to minimize flow disruption. These refinements reduced drag by approximately 8% compared to early double-hull designs, recovering most of the hydrodynamic disadvantage. Diving physics reveals why Japanese double-hull submarines took longer to submerge than American single-hull boats. When a submarine dives, it must flood ballast tanks until overall density exceeds seawater density. The rate of flooding depends on tank volume and vent size. Japanese boats had larger ballast tanks due to the space between hulls, requiring more time to flood completely. A Gato-class submarine could dive from surface trim to periscope depth in 60 seconds. Equivalent Japanese boats needed 90 to 100 seconds, a fatal disadvantage when aircraft appeared overhead. This slower diving time killed submarines throughout the Pacific campaign. The I-73 was caught on the surface near Guadalcanal in January 1943 by B-24 bombers. The boat had begun diving when bombs struck, penetrating the outer hull and flooding the engine room before the boat reached safe depth. 39 crew members died as the boat sank in 300 feet of water. Similar incidents claimed the IR-9, IR-31, and IR-182, all caught in the vulnerable period between diving alarm and reaching protective depth. The double-hull design that provided advantages in fuel capacity and depth charge resistance created a specific weakness against air attack. Japanese submarine commanders developed tactics to minimize this vulnerability. They posted lookouts specifically tasked with scanning the sky, independent of surface watch standers searching for ships. They installed radar detectors in 1943 that warned of American search radar, providing precious extra seconds to dive. Some commanders ordered crash dives at the first hint of aircraft, accepting the risk of damage from rapid descent to avoid certain death from bombs. But no tactical measure could overcome the fundamental physics. Double-hull boats needed more time to flood ballast tanks, and American air patrols grew more numerous as the war progressed. The battery installations in Japanese submarines reflected different design philosophy than American practice. Gato-class boats mounted batteries in two separate compartments, forward and aft of the control room, connected by heavy electrical cables running through the pressure hull. Japanese boats often concentrated batteries in a single large compartment to simplify electrical distribution and reduce cable weight. This centralized arrangement improved efficiency but created single-point failure vulnerability. If the battery compartment flooded, the entire boat lost power. American boats could potentially operate on one battery group if the other failed. Battery cell construction used lead-acid chemistry identical to American designs, producing 2.1 volts per cell when fully charged. A Japanese fleet submarine typically mounted 224 cells arranged in two parallel strings of 112 cells each. At full charge, this provided 235 volts DC at approximately 5,000 ampere-hours capacity. Running submerged at 2 knots drew roughly 70 amperes, giving 30-hour endurance if the batteries were not discharged below 20% capacity. Higher speeds increased current draw exponentially. For knots required 200 amperes, 5 knots needed 400 amperes. This exponential relationship meant sprint speeds underwater exhausted batteries within hours. The practical effect of battery limitations appears in patrol reports. The IR-176, patrolling off the Treasury Islands in November 1943, spent 42 hours submerged avoiding destroyer patrols. The boat ran at 2 knots to conserve battery power, creeping along just fast enough to maintain depth control. When batteries reached 20% charge, Commander Tonobe Yahachi had to surface despite knowing destroyers were nearby. The boat surfaced at midnight, started diesels, and began charging while making maximum speed away from the patrol area. 40 minutes later, radar-equipped destroyers detected the submarine and opened fire, forcing another emergency dive with partially charged batteries. The IR-176 survived this encounter but returned to base with batteries damaged from deep discharge cycles. Hull strength calculations determined maximum safe diving depth through complex stress analysis. Sea pressure increases approximately 1 atmosphere every 33 feet of depth. At 300 feet, pressure reaches 10 atmospheres or 150 pounds per square inch. The pressure hull must resist this force across its entire surface area without yielding. Japanese engineers calculated safety factors by testing sample hull sections in pressure chambers, gradually increasing pressure until the sample failed. Production hulls were built to withstand pressure 50% above rated depth, providing margin for manufacturing variations and battle damage. The deepest recorded dive by a Japanese submarine occurred in May 1944 when the IR-58 evaded destroyers by descending to 330 feet, well below its rated depth of 260 feet. Commander Hashimoto reported hearing the hull groan under pressure, bolts creaking and plates flexing visibly inward. The double hull construction likely saved the boat. The outer hull had already flooded from depth charge damage, equalizing pressure between the hulls and reducing the pressure differential the inner hull had to resist. A single hull boat at that depth would likely have suffered catastrophic implosion. Periscope optics represented one area where Japanese technology equaled or exceeded Allied standards. Periscope manufacturers like Nippon Kogaku ground lenses to tolerances measured in microns, creating optical systems with clarity rivaling the best German instruments. The standard Type 97 submarine periscope provided 1.5x and 6x magnification with a 40-degree field of view at low power, sufficient to search the horizon for targets. High power allowed precise bearing measurements for torpedo fire control. The periscope penetration through both pressure hull and outer hull required elaborate seal systems to prevent leakage, each seal representing a potential failure point. Sonar systems on Japanese submarines lagged significantly behind American and British technology. The Type 93 passive sonar could detect ships at ranges up to 10,000 meters in ideal conditions, but noise from the submarine's own machinery often masked distant contacts. Japanese boats lacked the sophisticated signal processing that allowed American submarines to classify contacts by propeller signature. This technological deficit forced Japanese commanders to rely more heavily on visual detection through periscopes, limiting their effectiveness in night attacks and poor visibility. The Type 95 torpedo carried by Japanese submarines represented their single greatest technological advantage. This oxygen-fueled weapon could reach ranges of 12,000 yards at 49 knots, compared to American Mark 14 torpedoes' maximum range of 4,500 yards at 46 knots. The extended range allowed Japanese submarines to fire from outside destroyer sonar detection range, then dive deep before counterattack developed. The oxygen propulsion system left a nearly invisible weight compared to the compressed air torpedoes American boats used until 1943, making evasive maneuvers difficult for targeted ships. But the Type 95's sophistication created maintenance challenges that partially offset its advantages. The oxygen flask storing pure oxygen at 3,000 pounds per square inch required meticulous care to prevent explosions. Even minute traces of oil in the oxygen system could trigger detonations that destroyed the torpedo and potentially damaged the submarine. Torpedo maintenance consumed enormous crew time, with oxygen systems requiring daily inspection and weekly complete servicing. The IR-176 suffered a catastrophic torpedo explosion in 1943 during maintenance that killed 6 crew members and nearly sank the boat. Combat loading procedures for Type 95 torpedoes took twice as long as loading American torpedoes due to the oxygen system's complexity. A Gato-class submarine could reload a torpedo tube in 15 minutes with a well-trained crew. Japanese boats needed 30 minutes per tube, reducing their sustained rate of fire in multi-ship attacks. This limitation proved critical during convoy battles when rapid reloading meant the difference between sinking 2 ships or 1. The doctrine that governed Japanese submarine employment evolved from pre-war naval theory that proved catastrophically wrong in practice. Imperial Japanese Navy planning assumed submarines would scout for the main battle fleet, track enemy movements, and attack damaged ships fleeing battle. This vision required submarines to operate near enemy naval concentrations, precisely where anti-submarine defenses were strongest. The double-hull design's advantages in fuel capacity and diving depth aimed to keep boats operational in these dangerous waters for extended periods. Reality diverged from doctrine immediately. American carrier task forces never concentrated in ways that made them vulnerable to submarine ambush. Instead, they operated in dispersed groups with destroyer screens that detected and attacked submarines before they could reach firing positions. Japanese submarines found themselves hunting targets that refused to appear, burning fuel patrolling empty ocean, while American submarines systematically destroyed Japanese merchant shipping. The I-6 attack on USS Saratoga in January 1942 illustrated both Japanese submarine capability and doctrinal obsession with warship targets. The boat patrolled off Hawaii for 3 weeks, submerged during daylight and surfacing at night to charge batteries and search for targets. On January 11, lookouts spotted the carrier operating alone, a violation of American procedures but fortunate timing for Commander Mizumachi Kennosuke. The boat, submerged to periscope depth, approached to 2,000 yards, and fired a 4-torpedo spread. 1 torpedo struck Saratoga below the waterline, flooding 3 boiler rooms and killing 6 sailors. The carrier survived but needed 5 months of repairs, removing it from action during the critical Guadalcanal campaign. This tactically successful attack highlighted strategic failure. The I-6 had expended 3 weeks of patrol time, consumed half its fuel, and exposed itself to counterattack for a mission that damaged but did not sink 1 carrier. That same patrol time and fuel could have supported systematic attacks against the merchant ships supplying Allied bases across the Pacific. Japanese submarines possessed the range and endurance to establish picket lines across shipping routes, stopping everything that moved. Instead, they concentrated near defended naval bases hoping for opportunities to attack warships. The mathematics of alternative strategies appear stark when calculated systematically. Japan deployed approximately 40 ocean-going submarines in the Pacific at any given time after mid-1942. Each boat could patrol for 60 days with double-hull fuel capacity. If positioned across shipping routes from the US West Coast to Australia, submarines could have attacked virtually every merchant convoy without Allied ability to reroute around them. Each submarine sinking 1 merchant ship per month would have destroyed 480 ships per year, potentially severing Allied supply lines completely. Instead, Japanese submarines achieved approximately 180 merchant ship sinkings across the entire war, less than 2 sinkings per boat total. American submarines, with inferior range but superior doctrine, sank 1,300 Japanese merchant vessels. The strategic asymmetry was total. Japanese boats designed for extended operations wasted their advantages while American boats executed systematic economic warfare that starved Japan of resources. Individual commanders understood this discrepancy but could not overcome institutional doctrine. Commander Arita Zenji, one of Japan's most successful submarine captains, wrote after the war that we knew American submarines were destroying our merchant fleet, but orders directed us to attack warships. When we encountered merchant ships, we were supposed to ignore them unless no military targets were available. This made no strategic sense, but orders were orders. The double-hull design's tactical advantages meant nothing when strategic employment was fundamentally flawed. The human factor in submarine warfare deserves examination beyond mere technical specifications. Japanese submarine crews endured conditions that tested physical and psychological endurance beyond most combat situations. A typical Pacific patrol lasted 60 days, 2 months sealed inside a steel tube barely wide enough to walk through without turning sideways. Temperatures inside submerged submarines reached 120 degrees Fahrenheit in tropical waters, with humidity near 100%. The double-hull design that provided tactical advantages also trapped heat between the hulls, creating an oven effect that conventional single-hull boats avoided. Crew berthing reflected these harsh conditions. Junior enlisted sailors slept in bunks stacked 3 high with barely 18 inches of vertical space per bunk. Officers shared tiny cabins with fold-down bunks and minimal privacy. The boat's motion in rough seas made sleep difficult even when exhaustion demanded rest. After 3 weeks at sea, most crews showed signs of heat exhaustion, weight loss, and psychological stress that degraded combat effectiveness. Food storage and preparation posed constant challenges on extended patrols. Fresh provisions lasted approximately 1 week before spoilage, forcing crews to subsist on rice, canned fish, and pickled vegetables for the remainder of the patrol. The double-hull design provided additional storage space for provisions, but tropical heat accelerated spoilage even in sealed containers. Crews returned from patrol with weight losses averaging 15 pounds per man, clear evidence of inadequate nutrition. Water rationing created additional hardship. Submarine distillation plants produced barely enough fresh water for drinking and cooking, with nothing left for washing. Crews went weeks without bathing, contributing to skin diseases and infections that compromised health. The I-177's patrol report from June 1944 noted that 32 of 62 crew members suffered from heat rash severe enough to impair duty performance. The double-hull design's better fuel capacity meant longer patrols, which meant longer exposure to these degrading conditions. If this story gave you a new way to see the Pacific War, like, share, and subscribe, and tell us which moment surprised you most. We'll return next week with another chapter in the war that changed the world. The Battle of Midway in June 1942 demonstrated Japanese submarine capabilities and limitations with crystalline clarity. Admiral Yamamoto deployed 15 submarines in a picket line northwest of Midway, positioned to detect and attack American carriers as they rushed to defend the atoll. The double-hull boats had sufficient fuel to remain on station for 3 weeks, maintaining continuous surveillance across hundreds of square miles of ocean. In theory, this deployment should have provided early warning of American movements and opportunities for devastating attacks on the carrier task forces. In practice, the submarine cordon failed completely. American carriers had already passed through the patrol line before Japanese submarines arrived on station, a timing failure that rendered the entire deployment worthless. When Japanese carriers engaged American forces on June 4, the submarines were out of position and unable to contribute. Only the I-168, commanded by Lieutenant Commander Tonobe Yahachi, achieved significant success, and that came after the carrier battle had concluded. The I-168's attack on USS Yorktown occurred on June 6, 2 days after the main battle. The carrier had survived bomb and torpedo damage during the air engagement and was under tow toward Pearl Harbor, escorted by destroyers. Tonobe approached Submerged, taking 4 hours to reach firing position due to aggressive destroyer patrols. At 1,531 hours, he fired a 4-torpedo spread from 1,500 yards. 2 torpedoes struck Yorktown, and a third hit the destroyer USS Hamman alongside, breaking the destroyer in half and sinking it within minutes. Yorktown finally sank the next morning, the only American carrier lost at Midway. This attack vindicated the double-hull design's advantages. The I-168 had remained submerged for nearly 20 hours during its approach and escape, far exceeding the endurance of earlier submarine designs. After firing, Tonobe took the boat deep, 300 feet, and sat silently on the bottom while destroyers dropped 60 depth charges overhead. The double-hull construction absorbed the shock waves better than a single-hull boat would have, though several outer hull plates buckled and flooding occurred in some saddle tanks. The boat survived and returned to Kwajalein for repairs, having demonstrated exactly the capabilities the design promised. Yet this tactical success highlighted strategic failure on a broader scale. Japanese submarines had concentrated near a major naval battle, precisely as doctrine prescribed, and achieved minimal results: 1 damaged carrier that might have sunk anyway, 1 destroyer, and no impact on the battle's outcome. American submarines would never make this mistake, instead hunting merchant shipping that sustained Japan's war economy. The double-hull design gave Japanese boats the range to patrol anywhere in the Pacific, but doctrine sent them to the places where they were least effective. The Guadalcanal campaign from August 1942 through February 1943 consumed Japanese submarines in a grinding attritional battle that destroyed their tactical edge. The Imperial Japanese Navy deployed submarines to attack American supply convoys feeding the Marine garrison on Guadalcanal, finally employing boats against merchant shipping in significant numbers. But American anti-submarine forces had evolved beyond Japanese capabilities to counter. Radar-equipped patrol aircraft detected surface submarines from miles away. Destroyer escorts hunted submarines with sonar arrays more sensitive than Japanese boats could evade. The casualty rate among Japanese submarines reached unsustainable levels. The I-19's attack on September 15, 1942, represented the peak of Japanese submarine tactical success. Commander Kanashi Takeichi spotted a task force built around USS Wasp and fired a 6-torpedo spread at the carrier from 1,000 yards. 3 torpedoes struck Wasp, starting fires that eventually forced the crew to abandon ship. The other 3 torpedoes continued traveling. The Type 95's range meant they remained dangerous far beyond the initial target. One struck USS North Carolina, a battleship operating 3 miles from Wasp, flooding several compartments and forcing the ship back to Pearl Harbor for repairs. Another torpedo hit USS O'Brien, a destroyer 4 miles away, causing damage that eventually proved fatal when the ship broke in half and sank during transit to the west coast. This extraordinary attack demonstrated both Type 95 torpedo superiority and the luck required for such success. 6 torpedoes fired in a single spread had damaged or destroyed 3 major warships, an achievement unmatched by any other submarine attack in any navy during the war. But luck played a role. The torpedoes that missed Wasp happened to intersect the tracks of ships miles away, something no fire control system could calculate deliberately. And even this spectacular success did nothing to alter the strategic situation at Guadalcanal, where American logistics continued flowing despite submarine attacks. The cost of operating near Guadalcanal became apparent as American forces adapted their tactics. The IA-31 was sunk on January 13, 1943, by New Zealand corvettes using depth charges and ramming attacks. The IA-1 went down on January 29 to New Zealand corvettes again, caught on the surface while charging batteries. The IA-18 disappeared in February, probably lost to mines or depth charges. These losses represented experienced crews and irreplaceable boats, the strategic reserve Japan could not afford to squander. The double-hull design that should have provided survivability advantages meant nothing against overwhelming American numerical and technological superiority. Post-war interrogation of Japanese submarine commanders revealed profound frustration with how their boats were employed. Commander Hashimoto Mochitsura testified to American intelligence officers that we had the best torpedoes in the world, submarines capable of reaching any target in the Pacific, and orders that wasted both. We should have been sinking tankers from the East Indies, cutting off oil supplies. Instead, we hunted carriers that were too well defended to attack successfully. This assessment from one of Japan's most successful submarine captains damned the strategic thinking that governed submarine operations throughout the war. American technical intelligence teams examining captured submarines after the war produced detailed reports that influenced American submarine design for decades. The report on the IA-400, designated JANAC Report SE-01, described the double-hull construction with both admiration and criticism. American engineers appreciated the structural efficiency of the figure-8 pressure hull and the operational advantages of external fuel storage. But they noted that construction complexity required skilled labor and time Japan could not afford during wartime mass production. The figure-8 pressure hull particularly interested American designers. Cross-sectional area calculations showed this configuration provided 40% more internal volume than a circular hull of equivalent outside diameter. For a submarine 300 feet long, this translated to 1,200 cubic feet of additional space available for batteries, fuel, or equipment. American naval architects investigated adopting this design for post-war submarines, but ultimately rejected it due to manufacturing complexity. Forming curved plates to the complex cross-section required specialized tools American shipyards did not possess. External fuel storage showed more promise for American adoption. The principle of storing diesel fuel outside the pressure hull freed internal volume for other uses, exactly the same advantage Japanese boats had exploited. American designers developed saddle tanks for diesel submarines of the 1950s, incorporating lessons learned from examining Japanese boats. These tanks used double-wall construction to prevent fuel contamination, an improvement over Japanese practice where single-wall tanks allowed seawater infiltration. Soviet submarine development followed a different path but reached similar conclusions about double-hull advantages. The Whiskey and Foxtrot classes of the 1950s used extensive double-hull construction with external fuel storage and figure-8 pressure hull elements remarkably similar to Japanese practice. Western intelligence spent considerable effort determining whether Soviet designers had captured Japanese plans or independently developed these features. Evidence suggests both factors played roles. Soviet forces captured Japanese submarines at war's end, and Soviet designers had their own tradition of double-hull construction predating these captures. The nuclear submarine revolution of the 1950s and 1960s rendered many double-hull advantages obsolete. Nuclear reactors eliminated the need for large diesel fuel bunkers. Nuclear propulsion provided unlimited underwater endurance, making battery capacity irrelevant. The fundamental constraint that had driven Japanese double-hull design, limited submerged time in diesel-electric boats, no longer applied. American nuclear submarines retained single-hull construction because the original advantages of double-hull design had been overtaken by technology. Yet specialized applications kept double-hull concepts alive in modern submarine design. Air-independent propulsion systems developed in the 1980s and 1990s required substantial space for oxygen storage and chemical reactors. Some modern AIP submarines use external pressure-resistant tanks for these systems, applying the same principle Japanese designers had used for fuel storage. The physics remains unchanged: storing materials outside the pressure hull preserves internal volume for more critical functions. Educational preservation of Japanese submarine history serves current generations through museums and memorial sites. The Yamato Museum in Kyoto displays a cutaway model of an I-class submarine showing the internal arrangement of the double-hull design. Visitors can see how the figure-8 pressure hull distributed crew quarters and machinery, how saddle tanks fit between pressure hull and outer hull, and how torpedoes were stored in external cradles. These displays teach engineering students that multiple valid solutions exist for submarine design problems, each with different trade-offs. The Japanese Maritime Self-Defense Force maintains institutional memory of these boats through its submarine school curriculum. Officers study pre-war and wartime submarine operations, learning both the technical capabilities the boats possessed and the doctrinal failures that wasted them. Modern Japanese submarines like the Soryu-class use advanced technology light years beyond World War II capabilities, but the fundamental lessons remain: submarine effectiveness depends on how they are employed, not just how they are built. The human cost of Japanese submarine operations appears in memorial records across Japan. The Yasukuni Shrine in Tokyo lists nearly 10,000 submarine sailors who died during the war, their names inscribed on wooden panels that families visit to honor the dead. These men operated sophisticated equipment competently, often displaying exceptional courage under terrifying conditions. Their deaths in futile attacks on heavily defended warships, when their boat should have been strangling Allied supply lines, represent strategic malpractice by the leadership that misemployed them. Individual stories illuminate these statistics. Lieutenant Mizushima Seiki, commanding the I-31, sent a final radio message as his boat was sinking after depth charge attack, have sustained mortal damage. Going down with ship. Long live the Emperor. The radio operator aboard the I-31's mothership copied this transmission, the last communication from a boat that vanished with all hands in the waters off New Georgia. Mizushima was 28 years old, an experienced commander who had survived 2 previous war patrols. His boat possessed the fuel capacity and endurance to patrol for months, but doctrine had sent it into confined waters where American destroyers had overwhelming advantage. The technical achievement represented by Japanese double-hull submarines deserves recognition separate from the strategic failure that wasted them. Japanese engineers solved real problems through innovative design. The figure-8 pressure hull distributed sea pressure efficiently while providing more internal volume than conventional circular designs. External fuel storage preserved interior space for batteries and weapons. Construction quality equaled or exceeded any other nation's submarine force. These boats performed exactly as their designers intended, diving deep, patrolling far, and surviving damage that would have destroyed lesser boats. But technical excellence cannot compensate for strategic incoherence. The Japanese submarine force fought the wrong war against the wrong targets using the wrong tactics. Boats designed for extended patrols were sent to defend naval bases. Torpedoes capable of 12,000-yard range were fired at point-blank distance where any torpedo would work. Fuel capacity sufficient for 3-month patrols was burned conducting 1-month missions near friendly bases. Every technical advantage the double-hull design provided was squandered through doctrinal rigidity that refused to adapt when circumstances changed. The comparison with American submarine operations reveals how doctrine determines effectiveness more than design. American fleet submarines had shorter range than Japanese boats. Their single-hull construction provided less protection against depth charges. They carried inferior torpedoes until 1943. Yet American submarines sank 5 million tons of Japanese shipping because they hunted merchant vessels systematically, attacked supply lines relentlessly, and adapted tactics when situations changed. Superior doctrine overcame technical disadvantage through systematic application of force where it mattered strategically. Modern military analysis treats Japanese submarine operations as a cautionary tale about focusing on tactical capability while ignoring strategic effect. Military academies worldwide study the Pacific submarine campaign to illustrate this principle. Japanese submarines won tactical engagements but lost the strategic campaign. American submarines lost individual battles but won the war through systematic destruction of Japan's maritime logistics. The lesson transcends submarine warfare. Technical superiority means nothing if employed toward strategically irrelevant goals. If this story gave you a new way to see the Pacific War, like, share, and subscribe, and tell us which moment surprised you most. We'll return next week with another chapter in the war that changed the world. The final legacy of Japanese double-hull submarine design extends beyond the Pacific War into the Cold War and modern era. American submarine designers incorporated specific elements of Japanese practice into post-war boats, particularly the concept of external ballast and fuel tanks that preserved internal volume. The Tang-class submarines of the 1950s featured saddle tanks reminiscent of Japanese design, though constructed with American refinements that prevented the fuel contamination problems Japanese boats had experienced. These boats represented the last generation of American diesel-electric submarines before the nuclear revolution transformed underwater warfare completely. Soviet designers went further in adopting Japanese principles. The November-class nuclear submarines of the 1960s used double-hull construction extensively, with the outer hull providing both hydrodynamic shape and protection for the inner pressure hull. Western analysts initially interpreted this as Soviet backwardness, clinging to obsolete design principles. Later analysis revealed sophisticated thinking. The double hull provided acoustic isolation that made Soviet submarines quieter than their single-hull American counterparts in certain speed ranges. The layers of steel and the air gaps between them absorbed machinery noise that radiated directly through single-hull designs. This acoustic advantage mattered enormously during the Cold War submarine confrontations. American submarines hunting Soviet ballistic missile boats relied on passive sonar to detect targets. Soviet double-hull boats proved harder to hear at low speeds, creating a tactical advantage that partially offset American superiority in sonar technology. The principle was identical to what Japanese designers had discovered about depth charge resistance. Layers of structure absorb shock and sound more effectively than a single barrier. Physics hadn't changed, only the specific application of physical principles to new problems. The Chinese Navy submarine force provides another example of Japanese double-hull influence persisting into modern times. China acquired Soviet-designed Whiskey and Romeo-class submarines in the 1950s and 1960s, all using double-hull construction derived partly from Japanese practice. Chinese designers maintained this approach in domestically built boats, reasoning that double hulls provided valuable survivability advantages even as other navies abandoned the concept. The Type 039 Yuan-class submarines, entering service in the 2000s, still use partial double-hull construction for specific sections of the boat where external tanks provide operational benefits. The engineering education value of studying Japanese submarine design remains significant in modern naval architecture programs. Universities in Japan, America, and Europe use Japanese wartime submarines as case studies illustrating design trade-offs between competing requirements. Students calculate structural weight versus internal volume, analyze hydrodynamic efficiency versus construction complexity, and evaluate tactical advantages versus strategic outcomes. These exercises teach that engineering involves optimizing for specific contexts rather than seeking universal optimal solutions. The preservation of actual Japanese submarine hulls serves both historical memory and technical education. The wreck of the IA-400 lies in approximately 2,500 feet of water off Oahu, where American forces scuttled it in 1946. Deep-sea surveys conducted in 2005 and 2013 revealed the hull largely intact despite decades of corrosion. The double-hull structure remains recognizable, with the outer hull collapsed in places but the pressure hull maintaining its figure-8 shape. These wrecks provide data on long-term material degradation under deep-sea conditions, informing modern submarine construction and decommissioning planning. Japanese maritime museums display recovered submarine components and detailed replica models that allow visitors to understand double-hull construction visually. The Yamato Museum in Kyoto features a 20-meter section of pressure hull cut from a scrapped submarine, showing the internal framing and external plating arrangement. Visitors can see how the figure-8 configuration distributed structural loads and how saddle tanks fit between pressure hull and outer skin. These exhibits make abstract engineering concepts tangible, showing how theoretical calculations translated into physical structures that men lived and died within. The strategic lessons from Japanese submarine operations influence modern naval planning across multiple navies. Military theorists cite the Japanese experience as a cautionary tale about the dangers of focusing on tactical excellence while ignoring strategic objectives. Japanese submarines possess technical capabilities superior to their enemies in specific areas: longer range, better torpedoes, deeper diving. Yet they achieved strategically insignificant results because doctrine directed them toward the wrong targets. This disconnect between tactical means and strategic ends appears in modern military planning discussions worldwide, invoked whenever capability development proceeds without clear strategic purpose. The human dimension of submarine warfare continues to challenge modern naval forces despite technological advances. Submariners today face many of the same psychological stresses Japanese crews endured: prolonged confinement, separation from natural day-night cycles, inability to communicate with family for months. Modern submarines have air conditioning, better food, and more comfortable berthing than World War II boats, but the fundamental stresses of the undersea environment remain unchanged. Studies of submarine crew psychology cite Japanese wartime experiences as data points in understanding how humans cope with extended isolation in hostile environments. The environmental impact of scuttled Japanese submarines raises ongoing concerns as hull corrosion releases oil and heavy metals into ocean ecosystems. The I-400 and I-401, scuttled off Hawaii, contained hundreds of tons of diesel fuel and hydraulic oil when they sank. As corrosion breaches fuel tanks, this oil seeps into the surrounding water, creating localized pollution. Marine archaeologists and environmental scientists collaborate to monitor these wrecks, assessing whether active remediation is necessary or whether natural processes will handle the contamination over time. These considerations apply to thousands of ships and submarines scuttled worldwide after World War II, representing an ongoing environmental legacy of the conflict. The technological trajectory from Japanese wartime submarines to modern nuclear boats illustrates how innovation can render entire categories of problems obsolete. Japanese engineers devoted enormous effort to maximizing fuel capacity and battery endurance within the constraints of diesel-electric propulsion. Their double-hull solutions were elegant and effective, extracting maximum performance from fundamental technology. Then nuclear propulsion eliminated the constraints entirely, making fuel capacity and battery endurance irrelevant overnight. This pattern appears repeatedly in technological history: enormous effort optimizing within constraints, then paradigm shifts that render the constraints meaningless. Yet the specific problems diesel-electric submarines faced haven't disappeared completely. Many navies operate conventional submarines because they cost less than nuclear boats and provide adequate capability for coastal defense. These modern diesel-electric boats face the same fundamental constraints that drove Japanese double-hull design: limited fuel capacity, limited battery endurance, need to surface for air. Some modern boats use air-independent propulsion systems that allow weeks of submerged operation, but even these face energy storage limitations reminiscent of World War II. The problems Japanese engineers solved remain relevant for navies operating diesel-electric boats today. The final assessment of Japanese submarine design must separate technical achievement from strategic employment. As engineering, Japanese double-hull submarines represented sophisticated solutions to real problems. The figure-8 pressure hull, external fuel storage, and quality construction techniques produced boats with genuine operational advantages in specific parameters. American technical intelligence teams examining captured boats acknowledged these advantages while noting the construction complexity that made mass production difficult. Soviet and Chinese designers adopted elements of Japanese practice, validating the technical soundness of the approach. As instruments of national strategy, Japanese submarines failed utterly. The boats performed exactly as designed, but doctrine employed them in ways that wasted their capabilities. Submarines built for extended patrols in remote waters concentrated near defended naval bases. Boats capable of strangling enemy logistics focused on attacking warships. The double-hull design's advantages in range and endurance meant nothing when boats operated in areas where those advantages provided no strategic benefit. Technical excellence cannot compensate for strategic confusion, a lesson as relevant to modern defense planning as it was in 1945. If this story gave you a new way to see the Pacific War, like, share, and subscribe, and tell us which moment surprised you most. We'll return next week with another chapter in the war that changed the world.